Stephen Hawking proved black holes aren't entirely black, but in doing so, he may have broken reality itself. For most of human history, black holes were not objects. They were absences, voids where meaning stopped. They were the universe's final eraser. Anything that crossed the boundary, matter, light, even time itself, was gone forever. No signal returned. No trace remained. The universe did not remember what fell in. And for a long time, physics was perfectly comfortable with that. Then one man looked at the darkest objects in existence and said something no one expected. They glow. His name was Stephen Hawking, and with that single idea, he created a contradiction so severe that half a century later, physicists are still arguing over whether the laws of reality can survive it. Because if Hawking was right, then black holes are not tombs. They are slow, quiet leaks in the fabric of the universe. And if he was wrong, then something even worse is true. The universe is hiding information from us. To understand why this matters, we have to go back to a time before black holes existed at all, before equations, before telescopes, before physics itself had a language. Long before scientists feared black holes, humans feared darkness. In every ancient culture, darkness meant uncertainty. It meant danger. It meant places where knowledge could not follow. The night sky was not empty. It was full of gods, monsters, and unanswered questions. And yet, even then, humanity sensed something unsettling, that the universe might contain regions where light itself could not escape. In the late 1700s, a quiet English clergyman named John Marshall proposed something radical. He imagined a star so massive that its gravity would trap light. Not because light was weak, but because gravity was overwhelming. He called them dark stars. There were no equations to prove it, no observations to confirm it. But the idea lingered. A century later, Pierre-Simon Laplace independently reached the same conclusion. Gravity, if strong enough, could imprison light. Still, these ideas remained curiosities, thought experiments, mathematical ghosts, because light at the time was believed to be made of particles, and particles surely could escape anything if they were fast enough. Then physics changed. In 1915, Albert Einstein published the theory of general relativity, and in doing so, he redefined gravity itself. Gravity was no longer a force pulling objects together. It was spacetime bending under mass. And suddenly, Michel's dark stars were no longer curiosities. They were inevitable. Just months later, a German physicist named Karl Schwarzschild solved Einstein's equations for a very specific case. A perfectly spherical mass collapsed beyond a critical radius. The solution described something shocking, a boundary beyond which space-time itself pointed inward, a place where time slowed to a halt, a surface from which nothing, not even light, could return. Schwarzschild wrote the solution while serving on the Eastern Front during World War I. He mailed it to Einstein from the trenches. He would die of illness shortly after. Einstein read the paper, and he dismissed it. Not because the math was wrong, but because he believed nature would never allow such absurdities to exist. For decades, black holes were treated as mathematical artifacts, convenient singularities, objects that made equations behave badly, but which surely could not be real. Then the universe proved otherwise. In the mid-20th century, astronomers began finding stars orbiting invisible masses, galaxies rotating around nothing, radiation screaming from regions where no visible object existed. Black holes were no longer theoretical. They were everywhere, at the center of galaxies, in the aftermath of dying stars, scattered across the cosmos like gravity wells punched through reality. And according to classical physics, black holes had one defining feature. They erased information. Once something crossed the event horizon, its story ended. And that was fine, until quantum mechanics entered the room. Quantum mechanics does not like erasure. At the most fundamental level, the universe remembers everything. Particles may change form, states may evolve, but information, the complete description of a system, is never destroyed. This isn't philosophy, it's law. Quantum theory depends on it. Without information, conservation, predictions collapse. Probabilities stop adding up. The math breaks. So when physicists combined quantum mechanics with black holes, they ran into a problem that was not subtle. General relativity said, information falls in and is lost forever. Quantum mechanics said that is impossible. Both theories were correct, both were experimentally verified, and both could not be true at the same time. This was the battlefield Stephen Hawking walked into, not as a revolutionary trying to tear physics apart, but as a man trying to stop it from contradicting itself. Hawking's fascination with time began early. He was drawn to boundaries, beginnings, endings. The question of whether the universe had rules or simply habits. At 21, he was diagnosed with ALS and given a prognosis of just a few years to live. The diagnosis did not slow his thinking. If anything, it sharpened it. Hawking began working on black holes not as monsters, but as thermodynamic systems, objects with entropy, objects with temperature. And that idea alone was unsettling, because temperature implies radiation, and radiation implies emission, which black holes were never supposed to do. In the early 1970s, Hawking began studying quantum fields near the event horizon, not inside the black hole, but just outside it. And what he found was something no one expected. Empty space is not empty. At quantum scales, the vacuum is violent. Particles constantly pop into existence in pairs. One particle, one antiparticle. They exist for a fleeting instant before annihilating each other and disappearing back into nothingness. Normally, this happens everywhere, but near an event horizon, something strange occurs. If a particle pair forms just right, one particle can fall into the black hole while the other escapes. The escaping particle becomes real. The black hole loses energy, and slowly, unthinkably slowly, it begins to evaporate. This was not speculation. It was calculation. Hawking derived an exact temperature for black holes, a precise radiation spectrum, a formula that said, unmistakably, black holes emit radiation. They glow. This radiation would be incredibly weak for large black holes, so faint that no telescope could ever detect it. But its existence mattered more than its visibility, because if black holes radiate, they lose mass. And if they lose mass long enough, they disappear entirely, which means black holes are not eternal. They die, and when they die, what happens to everything that fell in? This was the moment physics broke, because Hawking radiation appeared completely random. It carried no information about what entered the black hole, no memory, no imprint, no message. When the black hole vanished, the information vanished with it. And Hawking said exactly that. Information is destroyed, not hidden, not scrambled. Destroyed. The universe forgets. It was the most radical claim a physicist could make, and Hawking knew it. He knew it violated quantum mechanics. He knew it meant rewriting the foundations of physics, but he also knew something else. If information escaped, it would have to escape from inside the event horizon. And nothing escapes from inside the event horizon. Not even light, not even causality. Hawking chose the lesser contradiction, or so he thought. What followed was one of the longest and most bitter intellectual wars in modern science. A war over whether reality preserves truth or erases it. And the deeper physicists dug, the more terrifying the possibilities became. Because solving the paradox might require sacrificing space-time itself. If you're still with me, you're already deeper into this story than most people ever go. So take a second to subscribe. We do long-form science storytelling here, where the ideas don't just get weird, they get dangerous. And the next part is where the paradox stops being theoretical and starts threatening the foundations of physics. The moment Stephen Hawking published his result, the problem stopped being academic. It became existential. Because physics is not just a collection of equations, it is a promise that the universe is internally consistent, that what goes in can, at least in principle, be reconstructed from what comes out. Hawking radiation shattered that promise. If a black hole forms from a star, absorbs planets, light, histories, entire civilizations' worth of information, and then evaporates into a faint, featureless mist of particles, then the universe has erased part of its own past, not hidden it, not encrypted it, erased it, and quantum mechanics does not allow erasure. At first, many physicists assumed Hawking had made a mistake. The calculation was subtle. The math involved curved space-time, quantum fields, and limits taken in uncomfortable places. Surely something had been overlooked, but the more they checked, the worse it got. The math held. The radiation was real, and the paradox was unavoidable. This contradiction came to be known as the black hole information paradox. It wasn't a single problem. It was a fracture running through the foundations of reality. On one side stood general relativity, elegant, geometric, deterministic, a universe where space-time bends smoothly and horizons are absolute. On the other side stood quantum mechanics, probabilistic, discrete, unforgiving about information. Both theories worked. Both were experimentally verified. And black holes forced them to speak to each other. They did not agree. Some physicists tried to soften the blow. Maybe information wasn't destroyed, they argued. Maybe it was simply inaccessible. Maybe it remained trapped inside the black hole forever. But Hawking radiation ruined that hope. If the black hole evaporates completely, there is no inside left. No storage, no vault, nothing. Others proposed that information might be released at the very end in a final burst as the black hole dies. But Hawking's equations said otherwise. The radiation is thermal, featureless, memoryless, like smoke rising from a fire that tells you nothing about what was burned. Hawking did not shy away from the implications. He leaned into them. He argued that quantum mechanics must be modified. That unitarity, the principle that information is preserved, was not sacred. That the universe might not be reversible. That time might genuinely destroy information. It was a shocking stance, and it did not go unchallenged. Among Hawking's fiercest opponents was a physicist named Leonard Susskind. Susskind didn't believe the universe erased its own memory. He believed something else was wrong. Very wrong. Susskind argued that if information were truly destroyed, then quantum mechanics would collapse. Cause and effect would blur. Predictability would erode. Physics would lose its grip on reality. Instead, he proposed something radical. What if information is never lost, but also never really enters the black hole? What if the event horizon is not a passive boundary, but an active surface? According to Susskind, from the perspective of an outside observer, information is not swallowed. It is smeared across the event horizon, flattened, encoded. To someone falling in, nothing special happens at the horizon. They cross it smoothly. To someone watching from afar, the information never crosses at all. Both descriptions are true, but no single observer ever sees a contradiction. This idea became known as black hole complementarity. Reality depends on perspective. Not metaphorically, literally. It was a clever idea, but it came at a cost. It suggested that there is no single, objective description of what happens at a black hole. Reality fractures depending on who is watching. And even that wasn't enough, because the paradox refused to stay contained. In the late 1990s, a new idea emerged, one so strange that it sounded like science fiction: the holographic principle. Proposed independently by Gerard 't Hooft and Leonard Susskind, it suggested that all the information inside a volume of space can be described by data on its boundary. In other words, a three-dimensional world might be encoded on a two-dimensional surface, like a hologram. Black holes with their information-saturated horizons were the clue. If true, this meant the universe itself might be holographic. Reality as we experience it could be a projection, not an illusion, but an encoding. Then came a breakthrough that changed everything. In 1997, Juan Maldacena proposed a correspondence between two very different kinds of theories: a theory of gravity in a curved space-time, and a quantum theory without gravity on its boundary. They were mathematically equivalent. Different languages, same physics. This became known as the ADS-CFT correspondence, and it provided something Hawking radiation never had: a place for information to go. In this framework, black holes do not destroy information. They scramble it, mix it, spread it thin across the boundary of space-time. Nothing is lost, but nothing is simple. For a time, it seemed the paradox might finally be resolved. Hawking himself eventually conceded that information might be preserved after all. In 2004, he announced that black holes do not destroy information. He even conceded a famous bet. But the victory was incomplete, because no one could explain how information escapes without violating something else. And that something else turned out to be space-time itself. In 2012, the paradox returned with a vengeance. A group of physicists proposed a devastating argument now known as the firewall paradox. Their reasoning was brutal. If information escapes in Hawking radiation, then late radiation must be correlated with early radiation. Quantum mechanics demands it, but general relativity demands something else: that an infalling observer experiences nothing unusual at the event horizon. Smooth passage, no drama. The two demands cannot both be satisfied. Something has to give. Either information does not escape, or the event horizon is not benign. The conclusion was horrifying. If information is preserved, then the event horizon must be a violent place. A firewall of high-energy particles that incinerates anything attempting to cross. No smooth passage, no relativity. Einstein's equivalence principle, one of the most sacred ideas in physics, dies. And if there is no firewall, then quantum mechanics breaks. There is no middle ground. The universe must sacrifice something fundamental, either space-time continuity or information conservation. Physicists found themselves staring at a choice no one wanted to make. Was Hawking wrong to say information is destroyed? Or was Einstein wrong about space-time? Or was the entire framework we use to describe reality incomplete? Stephen Hawking watched these debates unfold. In his later years, he explored new ideas about horizons that were not absolute, about information leaking out in subtle, chaotic ways, about black holes not having event horizons in the classical sense at all. But even he didn't claim to have solved the paradox. At best, he softened it. At worst, he passed it on. Today, the black hole information paradox remains unresolved. Experiments cannot probe it directly. Telescopes cannot see it. And yet, it may hold the key to the deepest question physics has ever asked. Is reality fundamentally reversible? Or does the universe forget? Black holes were once thought to be the simplest objects in existence, defined only by mass, charge, and spin. Now they appear to be the most complicated, places where space, time, and information collide, where our theories stop agreeing, and where the universe refuses to explain itself. Stephen Hawking didn't prove that black holes aren't entirely black. He proved something far more unsettling. That when we push our understanding to the edge, reality pushes back. The black hole information paradox refuses to die because it is not a technical problem. It is a philosophical wound. It cuts into our most basic assumptions about what the universe is allowed to do. For centuries, physics was built on a quiet belief that the universe is, in principle, knowable. That if you knew the state of everything at one moment, you could reconstruct the past and predict the future. Black holes threaten that belief. If information can be destroyed, then the universe is not a perfect record. It is not reversible. It does not preserve truth. It edits itself, and that possibility terrifies physicists far more than any singularity ever could, because information is not just data, it is identity. It is the difference between one arrangement of matter and another, between a star and a planet, between a brain and empty space. If information is lost, then two different pasts can lead to the same present. History collapses, causality weakens, meaning itself becomes fragile. This is why Hawking's claim struck so deeply. He was not saying black holes glow. He was saying the universe forgets. Many physicists simply refuse to accept that. They believed, almost instinctively, that reality must preserve information, even if it hides it in ways we don't yet understand. But here is the uncomfortable truth. Every attempt to save information comes with a cost. If information escapes encoded in Hawking radiation, then that radiation must somehow know what fell in. But Hawking radiation is generated at the event horizon, far from the singularity. It is born from quantum fluctuations near the edge, not from the contents inside. So how does it know? How does the radiation carry a message it was never exposed to? This question has no simple answer. Some suggest that space-time itself stores information non-locally, that the geometry of the horizon encodes the data, that nothing is truly inside in the way we imagine. Others propose that space-time is not fundamental at all, that space and time are emergent phenomena, byproducts of deeper, more abstract structures. In this view, black holes are not holes in space. They are failures of our description, like bugs in a simulation revealing the limits of the code. The firewall paradox pushed this idea to its breaking point, because if firewalls exist, then falling into a black hole would be catastrophic, not gradually, not near the singularity, instantly, at the horizon itself. This violates one of the most tested principles in physics, that locally, the laws of physics are the same everywhere. If firewalls are real, spacetime is not smooth. It is stitched together from incompatible rules. And if firewalls are not real, then information must escape in a way that violates quantum entanglement, which means quantum mechanics, our most successful theory, fails under extreme conditions. Either way, something fundamental breaks. This is why the paradox has survived for decades, because every solution demands a sacrifice. Some physicists now suspect that the mistake lies not in black holes, but in our assumption that information behaves the same way in all regimes. Perhaps information conservation is not absolute. Perhaps it is approximate, emergent, context-dependent. Others argue the opposite, that information is sacred, but space-time is not. That space and time are illusions born from entanglement. That gravity itself emerges from information theory. In this view, black holes are not destroying information. They are reorganizing it in ways that feel like destruction to beings trapped inside space-time. To us, the irony is hard to ignore. Black holes were once thought to be simple, featureless, defined by only a handful of numbers. Now they appear to be the most information-dense objects in the universe. More like hard drives than voids, more like archives than graves. Stephen Hawking spent much of his life exploring the edges of knowledge. Time, origins, boundaries. In the end, he did not claim victory over the paradox he helped create. He acknowledged its persistence, its resistance, its refusal to yield. That may be his greatest contribution, not an answer, but a question so sharp it cannot be ignored. Because the black hole information paradox is not really about black holes. It is about whether the universe is fundamentally honest, whether it keeps records, whether the past exists in any meaningful sense, or whether reality is allowed to erase itself without consequence. We do not yet know the answer. Future theories of quantum gravity may resolve the paradox cleanly, or they may reveal that our current frameworks were never meant to coexist. That general relativity and quantum mechanics are approximations of something deeper, something stranger, something we do not yet have words for. Until then, black holes remain the universe's greatest confession, that when pushed to its limits, reality does not explain itself. It contradicts itself. And perhaps that is the final lesson Stephen Hawking left us. Not that black holes glow, not that information is lost, but that the universe, at its deepest level, may not care about our need for consistency. It simply exists. And sometimes it refuses to tell us why. The deeper physicists went, the more unsettling the picture became. Because black holes were no longer just objects, they were tests, stress tests for reality itself. Every attempt to resolve the information paradox forced physicists to confront a possibility they had quietly avoided for decades, that the universe might not be built the way we think it is. Consider what the paradox is really saying. A black hole forms from ordinary matter, atoms, particles, fields, each with a precise quantum description. As the black hole radiates, it releases particles that appear completely random. If the radiation truly carries no information, then two wildly different black holes could evaporate into the same final state. different pasts, identical presents. That should be impossible. In quantum mechanics, the present contains the past. Erase that rule, and prediction itself collapses. Yet black holes seem to demand exactly that erasure. This led some physicists to an even darker conclusion. Maybe the universe does not preserve truth. Maybe it only preserves probability. In this view, reality is not a perfect ledger. It is a process, a computation that overwrites itself as it runs. The past exists only insofar as it influences the present. Once that influence is gone, so is the past. This idea is deeply uncomfortable because it suggests that history is not fundamental, memory is not guaranteed, and existence is not cumulative. But physics has already hinted at this before. Entropy increases, time flows in one direction, information spreads out, becoming harder to reconstruct. Black holes may simply be the most extreme expression of this rule, not a violation, but a revelation. Others pushed the idea even further. They asked, what if information is preserved, but not in space-time? What if space-time is the wrong place to look? In recent decades, physicists have begun to suspect that space-time itself might not be fundamental, that it emerges from something deeper, something more abstract, entanglement. In quantum mechanics, particles can be linked in ways that defy distance. Change one, and the other responds instantly, not by signaling, but by correlation. Some researchers believe space-time is woven from these correlations, that geometry emerges from entanglement patterns. If that's true, then black holes are not tearing information apart. They are reorganizing the structure that gives rise to space and time. From this perspective, the event horizon is not a wall. It is a boundary between descriptions. Inside and outside are not places. They are perspectives. And Hawking radiation is not information leaking out of a hole. It is information being re-expressed in a different language. This would explain why the radiation looks random. Because it is scrambled beyond recognition, like a book burned and reassembled as smoke patterns. Nothing is lost, but nothing is readable. Yet even this idea has consequences. If space-time is emergent, then gravity is not fundamental. It is a side effect, a macroscopic behavior arising from microscopic rules. That would mean Einstein's theory, as beautiful as it is incomplete. Not wrong, but approximate, like thermodynamics before atoms were discovered. And that raises another terrifying possibility. If space-time is emergent, then it can fail, break down, disappear. Black holes may be regions where space-time stops making sense, not because it is extreme, but because the underlying structure no longer supports it. This reframes the information paradox entirely, not as a contradiction, but as a warning, a sign that we are asking questions in the wrong language. We ask what happens inside a black hole, but inside may not exist. We ask where information goes, but where may not apply. We ask when information is lost, but when may dissolve. In this light, Hawking's greatest contribution may not be Hawking radiation. It may be that he forced physics to confront its own limits, to admit that our most successful theories are incompatible, and that the universe does not owe us a single unified explanation. There is another layer to this paradox that rarely gets discussed, one that cuts even deeper. Because black holes do not just challenge physics, they challenge identity. Imagine an object falling into a black hole. According to general relativity, it crosses the horizon smoothly. From its own perspective, nothing special happens. From the outside, it freezes. Its image redshifts. Its information spreads across the horizon. So where is the object? Is it inside? Is it outside? Is it both? Is it neither? The paradox suggests that identity itself may be observer-dependent, that what something is depends on who is asking. This idea is deeply unsettling because it does not stop at black holes. If identity is observer-dependent at the horizon, then what about everywhere else? What about time? What about consciousness? What about you? Physics has always assumed that reality has a single, objective description. Black holes threaten that assumption. They suggest a universe where multiple, incompatible descriptions coexist, each valid, each incomplete, and none privileged. Stephen Hawking once said that his greatest mistake was betting that information is lost. But perhaps the real mistake was assuming that information behaves the same way in all contexts, that it must be local, that it must be stored, that it must be retrievable. The universe may not work that way. Information may be relational, distributed, non-local. Not something you can point to, but something that emerges from relationships. If so, then the black hole information paradox is not a problem to be solved. It is a clue, a message written in gravity and quantum noise, telling us that reality is not built from objects, but from connections. And black holes are where those connections are stretched to their breaking point. We are still far from understanding what this means. Experiments cannot yet test these ideas directly, but observations are closing in. Gravitational waves, event horizon imaging, quantum simulations, each new piece of data presses harder against the paradox. For now, the universe remains silent. Black holes still evaporate, information still matters, and the equations still disagree. Stephen Hawking didn't give us closure. He gave us a wound in our understanding that refuses to heal. And perhaps that is the point, because as long as the paradox remains unresolved, we are forced to keep questioning, keep doubting, keep pushing, not just against black holes, but against our assumptions about reality itself. The closer physicists move toward a resolution, the clearer one truth becomes. The black hole information paradox is not waiting for a clever fix. It is waiting for a transformation. Every previous revolution in physics followed the same pattern. Newton's universe gave way to Einstein's. Determinism yielded to probability. Absolute time dissolved into spacetime. Each time, the old theory was not destroyed, it was absorbed, and black holes may be demanding the next absorption, one that forces us to let go of ideas we treat as sacred. Locality, separability, even spacetime itself. There is a growing suspicion among physicists that the paradox only exists because we are insisting on asking classical questions of a quantum universe. We ask where information is. We ask when it escapes. We ask how it moves. But those questions assume information behaves like an object in space and time. And it may not. Information may be more fundamental than space, more fundamental than time, more fundamental than matter. If that is true, then black holes are not destroying information. They are revealing that information does not belong to space-time at all, that space-time is something information creates. From this perspective, the universe is not built from particles. It is built from correlations, relationships, entanglement. Geometry emerges from how information is shared. Gravity emerges from how information resists compression. And black holes are where that compression reaches its limit. The paradox then becomes unavoidable, but not contradictory. Information is preserved, but not in a form spacetime can represent, not locally, not causally, not intuitively, to beings like us, embedded inside spacetime, that feels like loss, like erasure, like a lie, but from a deeper level, nothing is missing, only transformed beyond recognition. This idea is unsettling because it removes the comfort of a single objective story. There may be no master narrative of reality, only overlapping descriptions, each valid, each limited, each blind to what the others can see. Black holes sit at the intersection of those descriptions, and they do not reconcile them. They expose their incompatibility. Stephen Hawking did not set out to dismantle our understanding of reality. He was trying to understand black holes honestly, without forcing the universe to obey our preferences. That honesty led him to a conclusion many could not accept, that perhaps information is lost. Later, he softened that stance, but the damage was already done. The paradox could not be undone. It had revealed a fault, line that cannot be ignored. And so the question remains, was Hawking wrong, or is the universe lying to us? The answer may be neither. The universe may not be lying, and Hawking may not have been wrong. We may simply be mistaking our descriptions for reality itself. Black holes do not violate physics. They reveal where physics stops working as we understand it. They are not errors. They are messages. Messages written in radiation too faint to see, in equations that refuse to agree, in horizons that do not behave like boundaries should. They tell us that the universe is deeper than space, older than time, and more subtle than truth as we define it. Perhaps the universe does not preserve information the way we expect. Perhaps it does not owe us reversibility. Perhaps meaning is not fundamental, only relation. What we call paradox may be perspective. What we call loss may be transformation. And what we call reality may be a surface phenomenon, emerging from something far stranger beneath. Stephen Hawking once said that the goal of physics is to understand the universe so completely that we would have no need for philosophy. Ironically, black holes dragged physics back into philosophy's oldest questions. What is real? What is preserved? What is lost? And is the universe obligated to make sense to us? We do not yet know the answers, but one thing is certain. Black holes are no longer silent. They glow, they whisper contradictions, and they force us to confront a possibility more unsettling than destruction, that the universe is not broken. It is simply not built for human intuition. And until we accept that, the paradox will remain, not as a failure of physics, but as a reminder that the deeper we look into the cosmos, the more it looks back and asks whether we are ready to understand it. If you've made it this far, you're one of the few who's willing to stare into the deepest contradiction in modern physics and not look away. So here's the real question. If black holes force the universe to choose between spacetime and information, what else have we misunderstood about reality? Subscribe for more stories at the edge of science, where the answers don't just change what we know, they change what we are. Till next time, stay curious.